Welcome back to Multivariate Calculus. In this video, we're going to be looking at volume integrals in rectangular coordinates. Volume integrals are the three-dimensional extension of area integrals, just as area integrals were the two-dimensional extension of traditional integrals. Let me get my head out of the way and let's draw a picture very much as we had before. If we're considering some three-dimensional object, and I'm going to treat it as a rectangular prism because rectangular prisms are relatively easy to draw. Although this is a particularly bad rectangular prism, I apologize. We can imagine somewhere within this rectangular prism, there is this tiny little piece of volume which may live something like that deep inside of the piece. And if we think about the coordinates here, we've got some little bit dx, we've got some little bit dy, we've got some little bit dz. And all told, that little piece of volume is a rectangular prism. So you calculate its volume as length times width times height, dz, dy, dx. And from here we can use Fubini's theorem the same way we had for area integrals in order to turn a volume integral into iterated integrals and solve from there. So let's consider a block of foam with variable density given by delta of x, y, and z equals x plus y plus z plus 2. Well, the mass of this block is going to be, in general, mass is volume times density. And since our density is constantly changing, we want to add up all the pieces, integrate over a region the density dV. And I just realized I'm a step ahead of myself. I forgot to write down where this block lies. We're looking at the block in the form of a rectangular prism with x between 0 and 5, y between 0 and 3, and z between 0 and 2. And so to calculate the mass of this thing, we can iterate that integral. We'll have x goes from 0 to 5. We'll have y goes from 0 to 3. We will have z goes from 0 to 2. Our function was x plus y plus z plus 2. And then we set up dz, dy, dx, as we always do. All right, integrating this thing with respect to z Notice that x, y, and 2 are all constant with respect to z. So we will have x plus y plus 2 all times z, and then z itself will give us a 1/2 z squared term. And we evaluate that when z is 0 and when z is 2, and we still have our dy and our dx. So again, we're using iterated integrals. We're integrating with respect to z, and then we'll integrate with respect to y, and then we'll integrate with respect to x. It's the same thing as area integrals, just more complicated because we've got 3 variables instead of just 2. All right, plugging in z equals 2 gives us something of interest. Plugging in z equals 0 gives us 0. That's kind of convenient. All right, so we'll have 2x plus 2y plus 2 times 2, which is 4. And then we've got 1/2 of 4, which is 2. And again, the other term is going to be when z equals 0, the whole thing becomes 0, which is not very interesting. And I guess we can clean up one more step because 4 plus 2 is 6. And then continuing our iteration, we integrate with respect to y. 2x and z are both constant with respect to y. And then 2y, well, the integral of y is 1/2 y squared multiplied by 2. You just get y squared. And we'll evaluate this when y is equal to 0 and when y is equal to 3. All right, when y equals 3, we'll be multiplying everything times 3. All right, so 2x times 3 is 6x, 6 times 3 is 18, and 3 squared is 9. And then when you plug in y equals 0, you get a whole bunch of zeros. I'm not going to even bother writing it down. We can clean up one more time. 18 plus 9 is 27. And we are down to a single integral. We know how to deal with this. We'll have 6 times 1/2 x squared is 3x squared. And then we'll have 27x. And we'll evaluate this at 0 and at 5. When you plug in 5, well, 5 squared is 25. 3 times 25 is 75. 27 times 5 is 135. And plug in 0, you get 0 back out. And 135 plus 75 is 210. All right. One of the things I'm sure you noticed here is that I am using some very simple limits of integration. And I will be perfectly frank with you, I'm using simple limits of integration because complicated limits of integration are too much of a bash your head against the wall kind of thing. You can do the same thing we do with area integrals. You can look at the coordinates and set up your limits of integration where the limits on z is a function of x and y, the limits on y are still a function of x, and then the limits on x are constant, and it will absolutely work. It's never fun. And quite frankly, when things get that complicated, I strongly recommend using computer software to integrate numerically instead. But understanding the process and understanding how everything is supposed to work is still important. And understanding that all of the applications we've talked about with mass, center of mass, and everything else still apply in the case here of 3 dimensions. So let's wrap up with a problem like this for you to try on your own. I would like you to find the triple integral over region R of f of x, y, and z dv for the function f of x, y, and z equals x, y, z, and the region R defined by 0 is less than or equal to x is less than or equal to 1, 0 is less than or equal to y is less than or equal to 2, and 0 is less than or equal to z is less than or equal to 4. All right. Take a couple of minutes, see where you can get to with that one, and I'll see you in the next video.